Okay, so let's look at this interesting exercise. So we're given a matrix A, which is 3 by 3, diagonalizable, and we're even given the eigenvalues and corresponding eigenvectors. So what does that mean, for instance? That means that if we were to take A times V1, which is 1, 0, 0, then we would get lambda 1, which is 3, times 1, 0, 0. This doesn't happen every day. We're supposed to be very excited when something like this does happen. Okay? So this is an eigenvalue, it's a number. And over here, V1 is a corresponding eigenvector of the matrix A, and it's a non-zero vector. That's important. Okay, so these are the corresponding eigenvectors and eigenvalues. A is diagonalizable, which means that A is similar to a diagonal matrix, and we love diagonal matrices. So factor A into a product x dx inverse, where D is diagonal, and use this factorization to find A to the fifth, right? Like fill this in. We might not exactly do this. We can, and we will. We will do this. So let's get into it. So there is a little bit work involved here. We might cheat a little bit, but we'll try not to. Okay, so let's start solving. So solution. Okay, so first of all, finding x and d is quite easy. So D is the diagonal matrix, diag, such that it has lambda 1, lambda 2, lambda 3 on the diagonal. So 3, negative 3, 2. Okay, just to be clear, this was just lambda 1, lambda 2, and lambda 3. And this notation, diag 3, negative 3, 2, is just like saying we have a 3 by 3 matrix with 3, negative 3, and 2 on the diagonal. Okay, this is the diagonal over here. Great, right, this part. Next, what about x? So x, I usually use P, but this time I used x. X is the matrix whose columns are V1, V2, and V3. Okay. In other words, and I used round brackets here, sometimes I use square brackets, it just varies depending on my mood. Both are accepted in the literature. So, but use whatever you may use in class or your personal preference. So 1, 0, 0, that's V1, 1, 1, 0, that's V2, and 0, 1, 1, that is V3. Okay, and this is an invertible matrix. These eigenvectors are basically a basis of our R3. Okay, great. And we know, right, this is just from the general theory, that A equals to this x times D times x inverse. Now, there's a question that sometimes students may ask, why don't x and x inverse cancel? Well, they don't cancel because it just doesn't make sense, right? Or matrix multiplication doesn't commute. There's no way that x inverse will reach x here. So we cannot assume that these cancel, okay? Great. Okay, and I just realized that I had a typo over here. We're trying to find a to the fifth. So I just corrected this. There should be a 5 over here. Okay, and now we're going to see something very interesting. So let's calculate a to the fifth, okay? And I'm going to show all of the work here. And at some point, usually in class, one skips some of these steps. But I want to show you everything. So a to the fifth is a to the power of 5, excuse me, is xd x inverse to the power of 5. But what is the power of 5? It's multiplying 5 times, right? So let's grab this and multiply 5 times. And technically we could prove this using an inductive argument. That's 4 times. We're running out of room. Can we fit this in? Of course we can. However, by associativity, of multiplication, we can drop all of these parentheses and have a little multiplication sign in between them. And each product, x inverse x, is just the unit matrix I3. Okay, so x inverse x is I3. So we'll replace all of the x inverse x with I3, but I3 times d is just d. So all of the I3s are just going to vanish, and we'll be left with 5 copies of d. So x d to the 5, the 5th power of d, times the inverse of x. Okay, so let's see what that means. Well, let's see what is x and d. So let's go back up here, and we have x and d over here. I'm just going to copy that. Let's bring this down here. Great. So we have that this is equal to x, right? This was x. Here's d over here. I could have written it with that diagonal notation. And it's to the 5th power times the inverse of x. Now, in theory, this is multiplying 7 matrices, right? I mean, 5 of these and then another 2. But actually, it's not that difficult. So we're going to duplicate this. Now, when we multiply a diagonal matrix, then we can actually just bring the power inside here. So let's actually do that in the next step. So we have 3 to the 5, right? That's 81, or no, it's not 81, excuse me. It's 243. Yeah, it's 243. Negative 3 to the 5, that's negative 243. And to the 5, it's 32. I would even leave it like this, but okay. Times the inverse of this matrix. So we need to find the inverse real quick. Okay, so let's find the inverse. So what I'm going to do is use Gaussian elimination, where I have I3 over here. So I3 is almost the matrix on the left. So I'm going to be a little bit lazy and copy and paste. But this is not I3. It'll be I3 in a moment. Great. So now let's use some Gaussian elimination. Now the first column is good. The only thing we are left to do is get rid of this and this. So we'll do that in 2 steps. Okay. So let's do the following. So I'm going to get rid of this using R2. So this is in row number 1. So let's do R1, which we'd like to change, becomes R1 minus R2. Great. So that will get rid of this 1 over here. So we're changing row number 1. That means that we're left with 1, oops, wrong color, 1, 0, and let's see, what do we need over here? It's 0 minus 1, right? So negative 1. You have to be really careful over, doing this part. It's not difficult, but it's very easy, to not be focused and make a mistake. I almost made one now. It's always good to check your work after you made a transition like this. So we had 0 minus 1 is negative 1. We had 1 minus 0, which is 1. We had 0 minus 1, which is negative 1. And we had 0 minus 0, which is 0. Great. And finally, we want to change row number 1 again. But this time, I'm going to use addition. So let's change that up to a plus sign. Yeah, great, so that looks a lot better. Amazing. And this bar, like, don't let this deceive you. We have to do the elementary row operation along the entire row. Okay, great. So we're changing row number 1. Oh, and we want to remove this 1 over here. So let's take care of this too. I just noticed that. So I also want to do R2 becomes R2 minus R3. Yeah, so I don't really like this operation. It's really not good to mix things up. So I'm going to change this, and I'm going to use this 1 over here to destroy these two. It's usually a bad idea to like mix rows up in the middle. So I'm going to use R1 becomes R1 plus R3. Yeah, so I'm going to use R3 to destroy these, right, to convert them to 0. Okay, now that's a lot better. So you see, you know, I didn't exactly make a mistake, but I made some moves that I didn't really like. So really one has to be just really, really careful when doing Gaussian elimination. It's easy, fairly easy, but fairly tedious, so there's plenty of room to make mistakes. Okay, so first of all, we didn't change row number 3, so we can duplicate that. Oh, well, actually, I already did duplicate it. Okay, these are 0. That's how we chose the elementary row operation, so those will be zeros. And let's erase anything that we're not certain of. So we're not certain of rows 1 and 2. Right, so let's take care of that now. So R1 becomes R1 plus R3, so that's quite easy. It's 1 plus 0, which is 1. It's negative 1 plus 0, which is negative 1. And it's 0 plus 1, which is 1. Great. And now let's move down to row number 2. So R2 becomes R2 minus R3. So 0 minus 0 is 0. R2 minus R3, 1 minus 0 is 1. And R2 minus R3, 0 minus 1 is negative 1. And what was this all about? Well, I'll tell you what this was all about. We started with an X and an I3. And we did some elementary row operations. And we finally reached I3 and some mysterious matrix Y. Well, it turns out this mysterious matrix is none other than the inverse of X. So we have found the inverse of X. This is the inverse of X. 1, negative 1, 1. 0, 1, negative 1, 0, 0, 1. So let's put everything together. So we have a to the 5th equals to xd to the 5th, x inverse. And that's just these matrices, which we calculated earlier. So that's x d to the 5th and x inverse. Okay, and now the only thing left to do, which is really tedious, is to multiply these out. Right, so I don't know if I want to do this. I could use some scythe. Now I've been doing everything by hand, which is fine. But at some point it might be smart to use a computer. So we have 243 here, 0, 0, 0, negative 243, 0, 0, 0, 32, times this inverse matrix. So I'll copy that right there. And let's see how far we can go without a calculator. So actually multiplying this by this is quite easy. So it'll multiply the first row by 243. So this will become 243 negative 243 and 243 again. Now hopefully we didn't make any computational errors, but it seems correct. But you can see that we can go a long way solving a problem, and somewhere along the line something might not be right, and then it's really, really depressing. Okay, and I mean, this part is not as important as the rest of the problem. And now we could, let's try to continue, right? So if we do matrix multiplication now, right? So I would multiply this by this. So that just gives 243. You can multiply the first row by this, so by the negative 243, negative 243. So that would give us negative 486. 110 times this will give us positive 486. It's kind of cool that we can actually solve everything by hand, but I would recommend at some point, using a computer. 011 times this column is just 0. 011 times this column just picks out the negative 243. 011 times this is just 243 plus 32, which is 275. And finally, the 001 will just pick out the last row, right? So we have 0032. Okay, so let's write out our solution. So A to the 5 is the matrix that we just wrote a moment ago. And we are amazing. And happy linear algebra. Have a great day.